Okay, so in the last lecture, we talked about abelian blocks, A, and also A and omega, big omega. And of course, well, it's also, well, with, of course, well, or actually just S, with A and omega. Or rather, the set or interval uh, F, which is some principle, and this S and omega is close to. So, and this is the upper bound for A and omega set. So that our principle holds. Okay, so the well-ordered principle of, holds, and that we're able to extend and make bigger and bigger infinities out of abelian blocks. And after that, we talked about relationships between different persons, right? So we have some metric, which I forgot the name of it. I forgot the name of the metric. Hold on. Rather, it's like it's a mapping, a morphism, a homeomorphism, not isomorphism. So psi that maps a tuple onto REL. And since REL, since n, natural numbers, subset of REL, and n is some subset of um some subset of R, then we can say that REL, or the intersection between REL and R, is non-empty. And this intersection is in fact M over here. So the intersection between REL and R is precisely N. So the thing that's in both sets. And so that means since we conclude these facts, we can say that our theorem 2 states now that a given if we were to construct a topological space out of an abelian block or with its topology, then we can say that this is a manifold. This is a manifold because, by definition, manifolds are topological spaces that locally resemble Euclidean space. Not only that, but the formal definition is that they are topological spaces that are homeomorphic in subsets of Rn. So a manifold M is homeomorphic to R n or R tuples and tuples of R. So it's a homeomorphic to Rn. So I said in the last lecture isomorphic, but in fact it's actually homeomorphic because we're mapping between two topological spaces, which is M and R. So yeah. So M is homeomorphic to Rn. And because M is homeomorphic to Rn, M is an N manifold. Okay. And N is the amount of bases used to describe, or yeah. So some more facts about manifolds is that the cardinality of a manifold is called its order. So the amount of elements inside a manifold M, so this here M, or well M sharp, is the order of M. So it's the order of M. And these things are described via atlases. So yeah. since I don't have the paper right now that or my notes right now concerning the Banach-Tarski paradox and the sh- the Schroeder Bernstein theorem, I think. Yeah, I don't have the paper right now or my note right now, so I'm gonna push that as the last lecture. So we're gonna sort of rearrange the course a bit here in the middle. And so today we're gonna be talking about F manifolds or femboy manifolds. So what is a femboy manifold? Now, you guys know what are donuts, right? And but the thing is, in topology, donuts are what we call toruses. Tori. So these things, donuts, 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 and these things are called tori. Tori, Tori, plural, torus, or singular. And what these guys are basically these guys are uh they're one of the most prime example of a manifold. These guys are called orientable manifolds. So this is an orientable two manifold. A manifold dimensions determines the amount of dimensions. But the thing is, a manifold's dimensions is not like how we usually treat dimensions. So you know how we live in a 3 or 4 dimensional space, and a flat sheet of paper is 2 dimensional space. The dimension of a manifold is actually n minus 1. So it's manifold minus 1. So some manifold that exists in 3 space is what is a 2 manifold. And a manifold that exists in 2 space is called a 1 manifold. So something like a circle, which we call S1, circle, which we call S1, is a 1 manifold. Well, this torus or donut is a 2 manifold. It's a 2 manifold. And then there's a 1, this is a 1 manifold, just a regular circle. And one good way that mathematicians define what a torus is a product space of 2 circles. So yeah, product space of circles. So you have S1, and what we do is take its product with another S1, and then we get some torus T. T, say in 2 dimensions. That's this circle S1 here, and then this second circle, and then we have ourselves a torus. And these things are also called surfaces. So actually, there are actually names for these manifolds. So 1 manifolds are called curves. So you can tell, yeah, it's a curve. It's a circle after all. So we can draw it on subcoordinate plane and describe it via coordinate plane and an atlas. Um, 2 manifolds now are called surfaces, and then 3 manifolds and above are just 3 manifolds and above. They don't have special nicknames. So something like a sphere is a manifold. So the Earth itself is manifold. It's a manifold. So a sphere is a manifold. This S3, well S3, it's called a manifold. This is a manifold. This is S3. Oh no, that's the shell 3. So yeah, S3, S3. S3 is a manifold. S3. S3 here, shell 3. So it's a shell, a 3-dimensional shell. Or B3. B3. Which is a solid ball of 3 dimensions. These guys are examples of manifolds. Okay. The reason why I say B3 or ball 3 is to distinguish it from S3, which is a sphere that has a hollow inside, while B3 is a solid inside. So it's filled to the brim. It has no volume, technically. Though it can store volume. It has volume, but it's filled to the brim with something. So it's a ball. So not really a shell. So those are examples of manifolds. Um, Any surface you can think of, actually. Something like the Pringles manifold. A saddle. A saddle. If I get it correctly. Uh, there. Something like this. This Pringle over here is an example of a manifold. And the thing about this manifold, the thing that's interesting about a Pringle chip, is that on one side, if we face it one side, it has negative curvature, and then if you face it the other side, it has positive curvature. Right? So it points upwards on one side, and then it points downwards on another side. That's what's interesting about these kind of manifolds over here. So in general, manifolds are a way for us to generalize geometric figures or shapes. So something like a triangle, regular triangle. A triangle is a one manifold. One manifold. Something like a tetrahedron now. A tetrahedron. Tetrahedron is a two manifold. Actually, the thing about surfaces and two manifolds is that they locally resemble Euclidean space. And then when they locally resemble Euclidean space, that means a part of them looks like flat two-dimensional space. So and also the four-dimensional thing or analog of this thing, or the three-dimensional analog of this entire thing, is something that we can describe in three-dimensional Euclidean space. Okay? But something like three-dimensional parabola or something that exists in parabolic space is something else entirely. Okay, so yeah, parabolic space or hyperbolic space is different. So we're mostly talking about Euclidean space, so three-dimensional now. So what you can think of manifolds is that they are basically shapes that we can flatten on a sheet of paper, and then we would still understand them and be able to continuously and define them in a well in a good way. Basically, we're able to define there are no holes and stuff like that. And now the thing with manifolds is that yeah, some of them contain holes, like T1 or T2. Torus. Toruses have one hole, and these holes are called the genuses of the manifold. So if a manifold has two holes, so I say something like this, something like a pair of goggles, this is a genus 2 manifold because we have two holes in it. So the holes in it are called the genuses. So a coffee mug, is a genus 2 manifold. Something like an N95 mask is a genus 2 manifold because we have two holes here, exactly two holes here. And something like a fidget spinner without, or just regular fidget spinner, is a manifold or two manifold of genus 3. So I mean, depends on the amount of appendages on your fidget spinner, but something like that. And so yeah. Now, how does this relate to our study exactly? Well, the thing is, um, when we abstract this to general topological spaces, so right, we're not thinking about shapes anymore, but rather abstractions of the shapes. So or points rather that satisfy the property of the shape. We start to run into manifolds themselves. So as I stated in the previous lecture, with theorem two, if we have a given A space, A topological system, so an abelian block or a topological system, or topological space, with A as its underlying set, and A as the set we're taking the topology of, then if it does locally resemble Euclidean space by having some continuous homeomorphism between subsets of itself and subsets of Rn, then yes, it's a manifold, right? So we have some continuous deformation from this topological space onto Rn. And if that is the case, then we do have a manifold. So now what if we have some femboy space, right? So you guys did the fundamental femboy group, right? So F equipped with some operation or combination, any operation you guys can think of. So now let's take this F here, this Mactal F, out of the out of the structure, and then instead have it as just some underlying set of some topological space. So now instead of equipping it with an operation, let's equip it with its topology. So there, let's equip with its topology. Now the basis for this topology is arbitrary. It can be in like we can think of that can be described. So maybe our basis for this topology can be the main position states, and that the others are basically just unions on these main position states, right? So we have some set of femboys, some femboy space or F space, and then we have its topology, and then we equip them together into one mathematical structure. We have ourselves a topological space. And now, what if we're able to map this topological space onto REL, right? So, so REL. Now the thing with REL is that it's a very broad thing. It doesn't describe only relationship like romantic type of relationships. Okay, it doesn't just describe romantic relationships, but rather um it can also describe things like unions, like communities, basically. Now, now since the femboy community is a community, it's a type of relationship, right, between multiple people that's not romantic. We can technically map this onto REL, and the word community is technically part of REL because it describes the relationship between a group of people with or a group of families, basically, and that relationship is basically as a community. They are a community. So that means we can map this onto here, and we can say that this structure is a community, or this F is some community REL. And so, like how we map a billion blocks or well combinations of these guys, right? We can map this onto REL2 or onto Rn, or actually just R, subsets of R. And a subset of R is n, the natural number. So we can map this F equipped with its topology onto n. And since n is a subset, or well, since n is a subset of R, then can map we can map this topological space onto R. So therefore, it locally resembles Euclidean space. So we can map it onto R because psi also maps this structure onto N, which is a subset of R. We can have we can also have F tuples here, so we can have multiple dimensions of femboy. So we can extend this concept, right? And instead have F tuples equipped with their topology. So we have some F tuple. So F product dot 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 product F, and then its topology. We'll just do that because it's the thing is right in there. So F tuples equipped with its topology. So now we can still map this. So let's say this is tuple n times, and then we now map this onto REL. Onto not onto REL tuples. So REL to the n. And then now, since we can do that, that means we can map this onto n tuples. Because n tuples is a subset of REL tuples, or n tuples of REL. So n tuples of n, the natural numbers, is a subset of n tuples of REL. So now we can map this multi-dimensional topological space onto n tuples cross n. It could just be one or more dimensions, right? So now we can assign pairs or one or more pairs onto their own separate, cardinality. So we know that that's the size, the population of the space, or what psi is to map our topological space onto n and thus Rn. So now psi can map our n-dimensional topological space onto tuples of R, and also I mean n tuples of R. So Rn. So now this is the actual definition of an F manifold here. It's a generalization, right? But it can still be one-dimensional Fanboy space here. It can still be a one-dimensional Fanboy space. And then it would still pretty much hold for R1. But this is a general definition of an F manifold, okay? So if our theorem holds and that we're able to actually map or know the population, we don't have an infinite population, it's a finite one. We have some seamless mapping between between our topological space onto Rn. And since we can map those n tuples of our topological space onto R, we have ourselves a manifold. And that's a great thing. So now, this is what we call an F manifold. So definition 6. Yeah, definition 6. Definition 6. An F manifold. Okay, an Fn. Which I will call Fn. Blackboard will is Fn, which is topological space. Is a topological space. Is a topological space. Which is what we define the wire network. You know that locally resembles locally homeomorphic to n subset of R n and onto the subset of R n. So that is an F manifold. That's definition 6. So now you guys understand the sort of importance of the previous one. So we now not only have 1 or 2 dimensions, but multiple dimensions to describe this thing. So now, how do we describe manifolds such as this, right? How do we describe manifold in general? Well, we do that, my fellow students, we do that with what is called an atlas. And what is an atlas? Well, you guys know what an atlas is. Well, in your general context studies, atlases are basically charters of the world, right? So they give us what the world looks like on a flat sheet of paper. They're basically maps, well, literal maps, not mathematical maps. You know, not functions, but like maps on a paper. Those are charts. I mean, those are atlases. Or the atlas is some book that gives us charts of the world. And the atlas is composed of charts or maps of the world. So flat, two-dimensional maps, which are called charts. So, like how we want to describe Earth via maps, we want to describe manifolds through atlases. And we describe atlases through charts. Now, an example of this would be B3 or S3. S3, so a solid shell, it's just a shell, can be described via this definition, which is x squared plus y squared plus z squared, such that xy or actually is equal to r squared. R squared, such that these 4 entries x, y, z are elements of the integers, let's say, or the real numbers. Let's say the reals. Okay, so this is an example of an atlas. So what we do is we grab the sphere and we squish it down. So what we do now is, instead of use this direct definition, we break it down now into unions of these things. So the union of x squared, such as x is inside R, plus y squared, such that y is part of the reals, plus z squared, such that z is an element of R. So now we can split them up into sums. And then, so this is equivalent to this. So this is our chart. And then this is our atlas that describes this. So it's some formula or some description or way of defining the object so that we're able to construct it via some algebraic means. So it's an algebraic formula and then some stipulations that define what the manifold is. So this is for a solid shell S3. Okay. Actually, this B3. This is for B3, a solid ball B3. So that's the atlas. It's the atlas, and then its splitted parts are the charts. So how do we describe an F manifold in this way? Well, it really depends on the shape that you're abstracting your F manifold into. If you want to abstract it in some unit ball, then definitely what we want to do, if we want it to be a unit ball, like let's say when I do start discussing about the Banach-Tarski paradox, I will be using the unit ball view, B3. We will define this as some unit ball, some solid unit ball here. And then, so now what we want to do is define it via these things. So F1 squared plus F2 squared plus F3 squared is equal some FR squared. Such that, well, these three things, which I'll just say dot 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 because it's so tedious to write, is some real or some part of some F space or part of our F space. Okay, so this is the most basic or trivial example of what our F manifold is. So this is called our unit F ball B3. So this is not really just B3, but we will call it FB3. So FB3. So the Femboy unit ball of 3 dimensions. So now, how about we call it? How about that's now defined the Femboy donut? I keep alluding to this thing in the previous lectures. The treating femboys as donuts, right? Yeah, let's do that. Let's make an atlas for it. So we know that S1 is a manifold, right? And its chart is basically x squared plus y squared. X squared plus y squared, and then such that xy is an element of the real numbers. This is our atlas for S1. So way to describe S1, right? And so we know that a torus P1 is equal to just the product of S1 with itself, or two S1s of varying size. Okay, so actually this is R equals R squared, right? Oh wait, I'll just fix this. Equals R squared such that X, Y, and R are elements of the real numbers. Okay. So now what we want to do is just take the product of this atlas with itself to obtain a torus. But instead of writing R here, I'm gonna write as A, and I'm gonna write the second one as B, because what we want to show is that this A and the other one B are not the same, so that the torus is not some ring of some sorts. Okay, so it's not some solid or some cylindrical circle, right? So now P1 is equal to x squared plus y squared equals r squared, or actually a squared, such that x, y, and a are elements of the real numbers. And then take the product between this, so the Cartesian product with this set, x squared plus y squared. So now we have some new structure here. Okay, so we have two structures inside one structure, equals b squared, such that x, y, and b are elements of real numbers. Okay, such that A squared and B squared, or rather one of these guys, are less than each other. So I'm going to say that A is less than B. So this here, this S1 over here describes the inside circle. So I'm going to draw it here. So this is the first S1 on top. So this is the top view of the manifold we want to construct. So it's here. This is the first S1 here with the B squared. This is B. And then the second one here is A. Now this A. So A is bigger than B. So it has to always be like that. It cannot be the same thing because it would just give us one original S1. So that's the condition. So it has to be that one of these guys are less than each other. Okay? So the thing is, if they're the same thing, T1 would just equal S1. All right. That's a great thing. That's a great. Now this is for a two-dimensional torus or a one torus. Now, if we want to define a T2 or a torus, a two-manifold torus or two-dimensional or a three-dimensional torus, I mean, we're going to just take the product of this, but instead we add that Z component at the end. So we have some three-dimensional space. We have a third spatial dimension. Okay. So just need to add that Z there and then just maintain the A squared and B squared and the condition that one of them is less than the other. So that's how we construct a three-dimensional torus. So I'm saying. So now instead we have S2 instead of S1. So since S1 is just a flat circle, S2 is some it's now some surface, so some shell. Not really S3, but S2. S2 is a two manifold, and since it's a two manifold, it's a surface, and that surface is of sphere. So we now just take the total of S2 and S2 to have a T2. So now we just add the Z component here because S2, the atlas is this. Equals say A squared. It's an element of R. Okay, that's our atlas here. We just need to add the Z squared component on here so we can construct a three-dimensional torus instead of just some flat, donut, And now to do that, it's pretty simple actually. What we do is just take the product of two F-Manifolds or two S manifolds. So now instead of a solid ball, let's have a shell. So now construct some solid shell, Fs one or two, and then now take that with this. So take the product with it some other one. One. We have ourselves our Femboy donut or donut Femboy, which is FB2. We're in FS2 or the A of FS2. So the A is say greater than the B, which is an element of this and it's not of that. So and then A and B of course describes the radius, the radii of FS2, FS1 and FS2 respectively. So from there, we now have ourselves a torus, a solid Femboy torus, or Femboy donut. There. So we just take this solid sphere here, solid Femboy sphere, or shell, Femboy shell, and then take their product to obtain this here, which is our Femboy donut. Okay. And so now the thing is, we haven't defined a boundary yet. What is the boundary of a Femboy, right? What is the boundary of this thing? So right, we cannot just continue defining this R and then these things. What is the boundary of this? Where does it all stop? Where does our formula stop? Right? Because someone can just say, well, you just continue the wherever it would look like a donut. It would look like some weird sheet that sort of goes in all directions, and then there's some donut in the middle, like some donuts wrapped in tinfoil, and then the tinfoil just extends out into infinity, right? Someone can do that. So we need to define a boundary for the Fanboy. Okay, so the simplest way to define a boundary is by like this. So we write a boundary to be this. In topology, we write the boundary to be this. This del sign here, and some m. And then this boundary is the maximum value anything can take. So we know that this m here is composed. Let's say it's S1. Okay, let's say it's S1. So we know that M is described to some representation. Shall say, oh, we'll say A1, but that's AN, which in, these guys are the ones that sort of dictate the form of M, and then F dot 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 dictates is the condition for these guys, right? So it's a manifold. So this is a representation of this manifold, right? So now we want to define a maximum value for this thing so that we don't carry on this sequence forever, right? So we stop at some value, and that maximum value will be AM, maximum value of N, M, which is AM in this case. So this is the last element that we describe M with. So we don't extend it onto infinity. I mean, yes, we can, but then we don't know where the boundary is for that manifold. So, and actually, if we do extend the dimension of a manifold, then that doesn't affect the boundary, to be honest. We still have some maximum value that the values that are well abstracted using these signs here or these variables do not exceed. So when we talk about surgeries or surgeries, yeah, cutting apart manifolds and then well sort of matching those parts with new manifolds, we usually describe manifolds now as this ordered pair M with its boundary. Wherein this M is a manifold, an N manifold, and then this del M or partial M is its boundary. So we need to specify a boundary for the manifold so that no one can just infinitely stretch it. Okay. So in the case of our F manifold, what we want to do is define some last femboy that the values do not exceed. And that last femboy is in fact F R. Pretty neat, isn't it? Because the values don't exceed this FR here. Okay. So right, if we have some our femboy donut, right? We have this FR here. And then we have three spatial femboys to describe all the femboys are position sticks, right? And then so now this is the value that they don't exceed. They cannot be greater than this. This is literally our boundary. So if I'm gonna do this intuitively, so if we have our F donut or F manifold, which is femboy donut, the boundary in this case is well, if we have our construction a while ago, just our regular T2, then our boundary is AB. So our of T2 is A and B. These are boundaries. These are the values that the points inside the manifold cannot exceed. That's our boundary. Now for our femboy manifold, if we define our femboy manifold with this atlas, we're gonna write it down. So our FT2, FT2 Torus 2 is equal to some our first one here. So F x squared plus F y squared plus F z squared. Um, yeah. Okay. Oh no, sorry. That is N. It's equal to some F r squared. So R1. So this is our first one. So this is the inside sphere, such that well these guys I'll just move down. This sum is equal to well our original F manifold or F space. Close and then cross of course. Well, I'll just repeat the same thing. Dot of dots equal to this is the same thing here. Equal to F squared R2 such that the dot element of our F uh, oh wait, yes, makes sense. and then such that f of r1 or fr1 is less than, oh no, squared pala, squared is less than fr2 squared. And then close the or close the structure. Okay, so there it is. This is our FP2. And now our boundaries is FR1 and FR2 in this case. In this F manifold here, there's one example of the F manifold, which is our F torus or our Femboy donut. Their boundary is FR1 and FR2. So the values don't go inside this hole. That's why it's a hole after all. It's not filled. And that's why there are no values out here. There's no tinfoil that or sheet that extends in all dimensions. That's why, or in all directions. That's why this thing is only a donut, a confined surface, because they literally cannot exceed these boundaries. Therefore, they're called the boundary. And so, for this, we can say that this del of fp2 is equal to fr1 squared and fr2 squared. And now we describe this manifold as fp2 equipped with partial fp2. And so that's the full description of our manifold over here. Oh, very heavy lesson. But this is really how the math works. But again, feedback would be welcome. Oh, my chargers were very dirty. Step on it. So F manifolds are awesome. And this is our mathematical description for a femboy donut. I know you guys probably didn't expect this, but I think you guys should have already expected something like this because this is already an advanced course and all that. But there's our femboy donut here. So we have three main position states here, or three basis femboys, right? And then we have some boundary. And then these are the boundaries of these things. Now, one last thing is that if we let these F1s and then the F2s be some number system like C, we can describe this in a more compact way. Because if you learn some abstract algebra, according to abstract algebra, a torus, which I will call this or something like that, right, can be described via this quotient, the complex numbers divided by the Gaussian numbers. You can check that out. You can do that yourself. You can do that yourself. Now this quotient over here, with this mod Ci describes a torus. If we let one of these guys, these guys are actually manifolds really on their own. Okay, you can project these guys or think of the imaginary numbers of some vectors in R2. That's our sort of projection or our homeomorphism between this C and Rn. And now for the Gaussian integers, it's the same thing, but then we now map it onto Z, just regular integers, which is a subset of Rn. So therefore, these guys are locally homeomorphic to Rn. And because these guys are locally homeomorphic to Rn, this, or their quotient, maybe their product even, are locally homeomorphic to Rn. And it just so happens, there's some neat coincidence, or some neat mathematics, that the quotient between the complex numbers and the Gaussian integers gives us a torus. I think Michael Penn made a video about this. It's a very neat video. This is where I got the idea from, actually, of this thing over here, this fact that, well, the quotient between C and Ci is a torus. So I find that very neat. So if we think of the space of all femboys to just be this C and then this Ci, and then second one, right? We just basically have a torus. We get an F manifold or a femboy donut. If we think the femboys are complex numbers, or if we want to describe femboys via complex numbers and some by Gaussian integers, then take the quotient of these two spaces, and then we get ourselves a topological space, which is a manifold, and it's a donut, femboy donut, which is great. Actually, I find it more compact to express it in this way. So yeah, but if you want to be more specific about what your manifold is or your femboy donut is, you definitely would want to follow what I said a while ago, or what I wrote a while ago about the the sets and taking the products between two spheres or two solid shells or two two manifold shells. So yeah, so I guess this is it's the end of this lecture. In the next lecture, I guess we're gonna discuss about abstracting femboys into shapes, and we're gonna take detours into set theory, I believe, to discuss about the Kirov-Argyle paradox, the Stephenson-Maxwell paradox, and Hilbert's femboy. Also, the Hilbert's femboy is one of four, I believe, four theorems that I derived from the Stephenson-Maxwell paradox. Very positive ones. And so the last lecture to conclude this course is talking about Bussy spaces, formally divided Bussy spaces. We're taking the Bussy set and then extending it to the next level, right? And now endowing it or equipping it with an operation. So yeah, and then so Bussies that we know, the Bussy sets or small just Bussies. Well, if we think of Bussies as some abstract mathematical object, they now become some element of our B space or Bussy space. So that's the concept of it. I'm still fleshing it out, but that's good for the end of this lecture. So really sorry if this lecture is very, very heavy. I know most of you out there don't have very rich or deep advanced math knowledge, but quick course in topology would actually help with this thing, and also a little bit of abstract algebra. That's all it takes really. And these things are very easy to understand so long as you guys have studied set theory. Okay, you guys know the notion of the sets, the operations of the sets, and stuff like that. You would have no idea. You would have no problem grasping this lesson. All right. So yeah. So I know you guys had to hear this so early, I mean, so late in this course, but you guys should know already know by now that this is an advanced course. All right. And we here at the Lyceum of St. Candice take our education seriously. We want you guys to genuinely learn from these things. Okay. And these are just, math concepts, glorified math concepts that are made to be more interesting or some sort like that. So it's like very serious advanced maths mixed with jokes in order for you guys to understand it or something like that. So yeah, that's it for this lecture and see you guys in the next one.